Okay, here is warm-up 9.4.1. First two problems say use the unit circle to find the exact value of these two different things. Okay, so I could type these into calculators, but they won't necessarily be exact. So exact means I want simple radical form and not a decimal approximation. Okay, sometimes you will get exact answers if you use if you just plug them into your calculator. But for sine, we're going to be looking at the y-coordinate on the unit circle, and for tangent, we're going to be looking at y over x. Okay, so I happen to have a unit circle right here. Look at that, how convenient. Okay, so let's find 5 pi over 6. So I'm looking at the radian measures. 5 pi over 6 is right here. So I want the y value here, which is 1/2. So this one, yeah, it would actually, if you just put it in a calculator in radian mode, it would give you 0.5 out. Tangent, we want y over x. So I'm at 210 degrees. So I'm looking at the y-coordinate over the x-coordinate. So I'm going to have negative 1/2 over negative root 3 over 2. Okay, now those 2's are actually going to cancel when I clean this up. But let's just take this piece by piece. I can write this as division. And in turn, I can write that as multiplication by flipping the second fraction around. So this is going to be negative 1/2 multiplied by 2 over negative root 3. Okay? And now when I combine this fraction, I'm going to get negative 2 over negative 2 root 3. Well, now the negative, you can see the negative 2's are going to cancel each other out, right? But I still want to show that the root 3's in the denominator, like that, right? I could have done that from the first step. I'd have negative 1 over negative root 3 over negative root 3, but a negative over a negative would be positive, right? And then the last step would be to put this in simple radical form. By rationalizing the denominator, I need to get that radical out of the denominator. So I've got root 3 over 3, and that is the exact value of tangent of 210 degrees. Okay, let's sketch a 700 degree angle in standard position. I'm just realizing this part A was on the last warm-up, but that's okay because we're going to go further and talk about the reference angle. So in standard position, the vertex is always at the origin, and the initial side goes straight to the right on the x-axis. And then we're going to treat this like a clock. So if I want a positive angle, I'm going to turn this around like so. If you wanted a negative angle, you're going to go in this direction. Okay? So if you want a 90-degree angle, then the second side's going to be facing straight up. But I want more than that, right? So if I'm going for 700 degrees, if I go all the way around, I'm at 360 degrees. So I still need to keep going, okay? If we go around twice, 360 times 2 is 720. Well, that'd be a little bit too far, right? So I'm going to go almost all the way around. I'm thinking I'm going 20 degrees shy of the x-axis, because if I go around the full 2 turns, that would be 720 degrees. So I'm going to go around a little bit less than that. I'm not measuring this with the protractor, but I want that to be 70 degrees shy of 720 degrees of 2 full turns. Okay, and you'd want to put the little spiral to show that you went around twice in that direction. Okay, the reference angle is the angle that the terminal side forms with the x-axis. It's the acute angle. So the reference angle, just think, okay, what's the shortest distance from this terminal side to the x-axis? Well, it'd be right in here, right? So that is going to be the reference angle. So I'm going to highlight this in pink here. This is my reference angle, okay? And I know I didn't measure out my angle, I was just eyeballing it. But the reference angle, if I did measure it out, I'd want that little slice to be 20 degrees, right? Because it was 20 degrees shy of 2 full rotations. So that is going to be my reference angle. And some people might think that that's negative because it's below the x-axis, but it doesn't matter where it is. Just think about measuring it with a protractor. It'd be a 20-degree angle. So 20 degrees is the reference angle. The reference angles are always positive. Think of measuring them with a protractor. Okay. All right. Number 4. The point 3, -5 lies on the terminal side of angle theta in standard position. Okay, so what I would recommend doing is making a little sketch, okay? I'm going to plot the point 3, -5 first on an xy axis. Okay, so I went 3 right, down 5, something like that. So here's the point 3, -5. Okay, and it says that's on the that point is on the terminal side. Okay, so I know my initial side is going to be something like this. I should really do this too. I should label these axes. I was being lazy there. X-axis, y-axis. Okay, so there's my initial side, and the terminal side is going to go through this point. Okay. Now, I don't know if I went around the positive direction or how many times, or if I went in the negative direction, but I know my angle is going to look something like that, okay? And the key here is making a right triangle out of this. So I'm going to use this as the hypotenuse of my right triangle, okay? And I'm also going to use the x-axis. So not the whole thing, but I'm going to use up to here, and then I'm going to draw a vertical line to complete my right triangle like that, okay? Now, I already know what 2 of the sides of this triangle are. I know I went 3 to the right there, and I went 5 down to get to this point, okay? So now what I can do is I can use the reference angle, because it doesn't matter which way you went around or how many times. All of these coterminal angles are going to have the same trig values. Okay, so I'm looking at this and thinking, okay, well, you know, I could get tangent from this because I could do opposite and adjacent, and that's great, but I need cosecant. So let's think about cosecant. So cosecant is going to be the reciprocal of sine. So cosecant is 1 over the sine. Okay, and the sine is the y value. Or you can think of, let's actually just think of it as, since we've got this triangle, using opposite and adjacent and hypotenuse. So the sine would be opposite over hypotenuse. So that means cosecant is going to be the reciprocal of that. So it would be hypotenuse over opposite. Okay? Now the opposite, I can already see that's -5. All right, but I don't know the hypotenuse yet, so I've got to do a little side problem for that. So let's find the length of this hypotenuse, and I can use the Pythagorean theorem. By the way, this is not a 3, 4, 5 triangle. This couldn't be 4 because this is 5, right? And the hypotenuse has to be the biggest piece. So it's a 3, 5, something else triangle. So Pythagorean theorem here. My A is going to, these are the 2 legs. They're going to, my A, I'll call that the 3, but you could write that it's the -5. Doesn't really matter. Those are interchangeable, but the C has to be the hypotenuse, right? So I've got 9 plus 25 equals C squared. All right, 9 plus 25 is 34. And then I'm going to take the square root of both sides. And I only want the positive root here. The hypotenuse is always going to be positive. So I've got root 34, and I'm thinking, is that in simple radical form? Well, it'd be 2 times 17, but no twins down there, so that's good to go. So that means root 34 is the hypotenuse. That's the missing piece. And so cosecant of theta then is going to be root 34 over -5. Or you could put the negative on top or in the middle, but it's a negative fraction. Okay, and that's the end of the warm-up, and I'll see you next time.